Here. So I'll be mostly talking about weather and climate simulation today. So I think for this audience, I don't have to stress too much on the importance of anti-climate change. So this is the from IPCC report. So basically what we have here today is about 1 degree warmer than our past climate. So even we continue our if we continue our current effort to reduce greenhouse emissions, then we will still going to about 3 to 4 degrees warmer by end of this century. And if we don't do that, we can go to 6 to 7 degrees, which would be worse. But even in the most optimized, even in the most optimized pathways, we still will see about 1.5 degrees or warmer by end of the century. So the conclusion is that we are never going back to the climate of our past. So we have to learn how to adapt to climate change in the future. And in order to adapt to the climate change in the future, we need to answer a few questions like whether there will be more droughts in the Horn of Africa, whether there will be more hurricane season in the North America, whether there will be a failed monsoon, summer monsoon in South Asia, will be there more wildfires in Australia, or more floodings in Europe. So in order to answer this question, so the answer to those questions are probably yes to all of these questions, but the question is how intensified it will be. And in order to know that, we need to run a lot of high accuracy simulations to help us to understand the climate change in the future. So traditionally, scientists have been relying on numerical models for decades. But there are some challenges, especially challenge one is the massive computer required to solve this system. So it's a complex system to simulate weather or climate. It involves hundreds of coupled nonlinear partial differential equations. There are couple interactive components, the atmosphere models, the ocean models, ice models, and etc. It's a very complex system. And also we want high resolution in order to have high accurate predictions or projections. So if we want to achieve a 1 kilometer resolution, then we need to solve a system of 10 to the power of 12 degree of freedom. And we can only solve this kind of problem by the year of 2060, given the current projection of how hardware is progressing today. So, and not only we want higher resolutions, we also want to have larger ensembles. So more ensemble numbers give us a better accurate, more accurate estimation of the uncertainties of our projections and predictions. So all this add on to the challenge one, the mass compute are needed. So the second challenge is the expertise we needed. So numerical weather forecast prediction has been operational for decades. There's a lot of experience accumulated in this domain, and the AI is just getting into this domain. So there are domain expertise we needed to develop state-of-art models and also configure the models for target domain. We also need operational expertise, where we need to choose the right initial conditions for the ensemble calibration. So on the left-hand side is an example of weather temperature forecast in the Central Europe region. So the red curve is the uncalibrated forecast, and the blue curve is a calibrated forecast. And we can see if the model is not calibrated, the forecast can be off by a lot. So the third challenge is that we need to run simulations to answer what if questions. So we have different questions in order to make policies for different regions. So this is an example from IPCC report. There are simulations run to forecast the climate change according to different shared socioeconomic pathways, which tell us how much we control the greenhouse emission reductions, then what kind of climate future we will have. But this is still quite limited. We need to run a much higher resolution for more accurate projections, and also we need to run more scenarios in order to understand different situations. So challenge 4, I would say, it's also as much a data problem as a compute problem. So we can easily talking about more than 100 petabytes or even more data. So storing, accessing, and analyzing data are a huge challenge. So for those who have experience working with ER85 data, downloading one parameter can easily take you 1 day or even if not a week. So there are hundreds of parameter variables available for you to play with. So that's the kind of challenge we are dealing with, the amount of data. So not only the data size is big, and we also have different sources of data. So data generated by different models, they can be generated on different grid structures, and also the data they capture can be different. So some models capture the instant value of that time. Some models actually capture values over interval. So it's an average value, for example, precipitation over 6 hours, for example. So different models generate data differently and capture the data differently. How we can make use data from different sources is another huge challenge to tackle. So last challenge I would say is given the ocean of data we currently available, how to actually explore and analyze this data. So traditionally we can only do this kind of two-dimensional control plot on one variable, which is this kind of static charts are very limited. So in order to get more insights from this huge amount of data, we need the right tools to have three-dimensional visualization and also interactive visualization to get more insight. So those are the challenges. So at 2021, our CEO announced the Earth-2 project. So it's a vision to build a digital twin Earth with AI technology. So there are mainly three pillars. One is a supercomputer to run the simulation. Then there's an AI algorithm, and also a visualization platform. So in the center of Earth-2 platform, there are really mainly four blocks. So first is the GPU acceleration. So we are working with a major numerical code developers to make their code running on GPUs, as mentioned earlier. So it's still important to accelerate these numerical models, which has been operational. And some of the data is going to generate by this numerical model to train our AI model. So for the AI model, we have the training component and the inference component. So for run this AI training and inferences, we developed this modular platform or framework. So it's an open source framework, mostly catered for AI for science applications. And the weather and the climate is one of the focus areas for its application. So after train, so this is a very highly abstract framework. So all the AI component has been optimized for GPU running on multi-node, multi-GPU. So it's very easy for use for domain expertise. So scientists, not necessarily for AI domain, you can still quite easily get on hands-on with this kind of framework. That's what we want to offer to scientific community. So we also have this AI enterprise cloud solutions where we can host our AI models on the cloud. So we can make this kind of technology more accessible for a larger audience. So currently, most of the climate and weather research are very restricted to a few handful national centers with supercomputers. But if we can host it on cloud, then more people can working on this kind of technology at different levels. Lastly is the visualization. So we do interactive visualization with our platform called Omniverse. So it utilizes OpenUSD data format to create a 3D scene. And it also works with AI models so that we can create interactive visualization with AI models. So with these three blocks, we build our digital twin. So AI weather models will be the game changer. So especially within recent 2 to 3 years, there's a huge improvement in AI weather models. Not only is approaching the state-of-art accuracies the operational numerical models are achieving, it's also a lot faster than the numerical models. So current state-of-art, we can reach 4 orders of magnitude faster than the traditional numerical models. So that means we can do a forecast in near second, almost near to real time. So this allows us to run the simulation at much cheaper cost, and much shorter time, and open up all the possibilities to explore a lot more scenarios, weather scenarios. So one of the key milestones for the Earth-2 project is our AI weather model called the Forecast Map. So it's based on the vision transformer architecture, and in between we replace these spatial mixing layers with our Boolean neural operator. So what Boolean neural operator did is to project the input into the Boolean space. So we learn the mapping between spectral space and we project it back into our dream space. So that intuitively give us the learning about the relationship that is naturally invariant. So it doesn't impact by the discretization because we are learning in the vector space. So we train this AI model with ERA5 data at 25 kilometer resolution at 6 hourly time steps. And we separate them into training, validation, and test sets. And we train it with roughly about 20 variables. Some are surface variables, some are upper atmospheric variables at 13 selected pressure levels. So our result was quite good, approaching the accuracy that IFS operational model for a forecast up to about 1 week. So the example here is a prediction on T850. So we can see both in the anomaly correlation coefficient or in the IMS-FE metric, both our models are performing quite comparative to the IFS output. So we announced our forecast net in early 2022. Then there's a lot more companies that start to invest into this domain. So Huawei announced the Pango in the late 2022, which is also a transformer-based architecture and also reach quite competitive accuracies compared with numerical models. Then just 1 month after, Google announced GraphCast, which is a very interesting graph neural network-based architecture. And it has this multi-level architectures that which is unique to the graph neural networks. They also reaching a competitive performance with numerical models. So we had a major update last year for our forecast net. So we are at our forecast version 2 and now. So what's new is the spherical neural operator. What it does is we actually tap on the spherical harmonic transform. So you can see spherical harmonic transform as a Fourier transform on a sphere. So because the data for climate weather is on a sphere, so it allows our AI model to run much more stable than our classical Fourier transform based model. So our original model can do forecast up to 2 weeks, and the new model can allow us to run simulation up to 1 year quite stably. So this put us one step closer to an AI-based climate model. So our target is to run it for decades that what we need to do a climate forecast. So with this state-of-the-art AI models that allows us to run a number of examples. So for example, it's very important for catastrophic models. We need to estimate the expected loss. So some of the rare events, extreme events, they can be rare, but they have a high impact. So we need to consider this model because once they happen, the impact will be huge. So one example is the Hurricane Sandy took place on 2012 in America. So if we only run 50 memorable examples, then our projection will be in between these 2 yellow lines. The hurricane will never hit America. But on the right bottom is the actual track of the hurricane. It turned left and hit directly in New Jersey. Cost estimated $70 billion loss and more than 400 lives. So if we could have run 1,000 member examples, then the prediction was between the red lines, and we will be able to prepare for the potential cost that it will be hit. Okay. So we're not only working on the global models, we are also working on regional models. So this is another example. We have built a generative model based on diffusion models. We test it on the Taiwanese region. So we get the regional high resolution data from the Taiwanese bureau. And we take the input from the global output, then we train it with the regional high resolution models. So we supervise it from 25 kilometer resolution into a 2 kilometer resolution. So if you look at the graphs, on the left is the ground truth, on the right is generated from the diffusion models. We can see the output from the diffusion models can capture a lot more fine scale features compared with the global regression model. So the global regression model tends to have much more smoother output, and the diffusion model is able to improve it. And not only it's giving a better output, it's also a lot faster and a lot more energy efficient compared with the traditional numerical models. Okay, so with all these innovations, we are also trying to operationalize all these AI technologies. So for the us2 projects, we are trying to operationalize three services. One is a numerical simulation as a service, then in the center will be AI as a service, and also visualization as a service. So we just announced the availability of AI as a service now. So we have early access if you are interested for AI as a service, but the simulation as a service and also visualization as a service will be coming soon. So, because of the time, I can't talk too much, but you can Google us too and modules. We have home pages for them, and there's a lot of documentation with a lot more details. So for developers who are interested in private application development, we have the early access for the cloud services and also APIs available for the cloud service. For researchers, we have over repository. Actually, we are trying to compare all different AI models from different developers, trying to compare them on the equal ground. So if you read the papers, everybody is doing their own experiments and tests. So it's really important to put them together to run and benchmark against each other with a common set of benchmarks. So I want to end my talk with this amazing demo available online. So this is an interactive demo we built with Omnibus Cloud. The data is from simulation data from ICON. So that's the kind of a digital twin we are foreseeing that will be built as a digital twin of us. So thank you very much.
Question? Yeah. Very impressive. Did you train your model based on the reality 5?
Yeah.
Well, with the reality 5. But
yeah.
We all know that the benchmark is problematic. So here another, for example, you can clearly underestimate the especially with the extreme rate, and also the temperature solution. For some extreme that are 2 degrees at least. So the benchmark is problematic. How do you handle that?
Yeah, so that's so basically he was the question was that the EIE5 benchmark data is itself is already problematic, especially for precipitation, right? So okay. Yeah, so that's the limitation that we have to deal with today. So the most available data is EIE5, so we start with the EIE5 data. So there are a lot more problems with the AI model that the scientific community probably not agree with us. So that's why we need to work together to understand that what are the concerns you have and how we can address when there are data available for us to actually to improve this kind of process.
Thanks. Very interesting talk. So I've got a few questions and comments. So my background is research. So I was really looking for what is NVIDIA doing in a climate long-term fight. And your talk was a lot about climate change. I just wanted to make a few comments because what you didn't mention was that the community is already doing a lot of what you said for quite a while. The public model inheritance project has been doing this for decades, creating petabytes of data that's been analyzed, visualized. That's the backbone of every IPCC report. Nonetheless, we are now all looking towards ML and AI to provide additional solutions to make everything cheaper. But I just want to say that there's a lot of that information and capability out there, and producing information that is already very getting more and more certain in terms of projections. You mentioned the new system that NVIDIA is building, but when you say on the climate timescale, you go out to 1 year, and that you're saying this is the system that we're imagining the actual long-term runs. And this is exactly what I want to understand. What's the plan with NVIDIA, how to work this? Because we all know if you do want to do long-term runs, you need to bring in the forcing data of future scenarios. And this is the trick. So I'd like to understand what's the plan in NVIDIA to support long-term climate runs, but not just running out the current system. So you know that may be possible, and you showed it, and then it'll probably break down. But how do you ensure going along scenario.
So one thing is we will continue to improve the AI model to make it more stable for long time running. And also we are discussing about training the AI model with DMIT6 data. So that will be the climate data rather than weather data. So we hope that to learn from the climate data will actually help us build a better climate model rather than weather forecast. So that's the kind of thing we are doing at the moment. Question? Yes, yeah.
Yeah, we have Matthew. I guess one question for your last number. You have a very beautiful image showing your, super resolution. You have a huge model for, okay, this one. I'm just curious, like the last one is the result you got. Right?
Yeah.
And are you talking about like the super result both the spatial and also temporal resolution? Because I see some kind of view in the last one.
No, so it's just spatial. So that is temporal is coming from the input data. So we have a series of input data. So for every time frame, we'll do a super resolution. Then we have a series of super resolution outputs, and we get the accuracy.
I see. Then in this case, your ground truth is actually static, right? But then your somehow the generated data are actually dynamically changing. Is it because the nature of randomness of your diffusion model is that I'm just curious.
Yeah, I'm not very sure about this output. I'll get back to you.
Oh, thank
you.
Yeah, I'm Trevor from NTU. So my question is about the differences between other approaches. Like presently we have destination art project in European Union and also the digital twin in NASA. So I'm just curious, what is the major differences like between those projects and your approach, and what is the differences in terms of applicability?
So we get inspiration from the European digital twin destination project as well, but that project was mostly based on numerical models. But for our emphasis was to build an AI digital twin. Yeah, I think that was based on Icon. That's a numerical model based digital twin. But for us, we want to build an AI model based digital. We have one chat. Will the slides be made available to attendees? Yeah. Yes, the answer is yes. We're going to make the slides available to attendees. Yes, Steve?
I have a question.
Do you want to use a microphone on the table?
So thank you very much for the talk. And my question is not only for you, but all the speakers, because what I listened so far that we always highlight the speed by using the AI, right? But we would like to have more than just the speed, because we can enjoy the GPU by running more. And then when you are getting the better computation for AI, you also get the better computation for traditional models as well, right? So now my question is, what we can do more than just repeat what we traditional model can do. That is something important, especially for some of the extreme event that we cannot predict by the traditional model. And AI help us because, for example, in my research, we try to use AI to recognize more association between the pollution exposure to some of the disease that we cannot find by the traditional statistical models. So how can AI do more than just replace what the traditional CTM or climate model do? This I think it's very important that we should explore. Second thing is we can produce the output faster, but can we interpret the results? For example, if you have shown the fancy video, can we explain the physics behind that? Is I think also important for weather forecast, that we don't want just have the output, but explain the development by like traditional like physics and visuals. So do you have any thought on that? Not only for your office.
Yeah, I think it's a very good comment. I don't have a solution for that, but it's an ongoing topic in research. There are like building informed models. There are hybrid models where you put AI models in numerical models, or you put numerical models into the AI models. all the efforts trying to have physical information into the AI model so we can like have more trust or confidence in the AI model. They also works on explainable AI, which is still ongoing research. So I don't have a solution, but it's something that people are actively looking at.
No more questions. Let's thank our speaker. Move on to our next speaker, Dr. Noel Ulloa. Noel is a research fellow at the Moore Sensing Lab at the Prof for Singapore at Nanyang Technological University. He did his PhD at National Central University in Taiwan, and he's going to talk about his efforts to build a framework to let his colleagues to easily try using AI tools that are off the shelf available or in-house developed as a module to plug in and how to test it.
Okay, good morning, everyone. My name is Noel. As Professor Samuel said, I am a research fellow at the Remote Sensing Lab at EOS. And today I want to share with you our lab's current efforts to lower the barrier of AI for geospatial research. So I guess most of us here can agree that AI seems powerful, very promising, but it's not always approachable. If you're an AI practitioner, it's very likely that you have had a colleague, a manager, or students approach to you and ask you questions like, how do I get an AI model to work with my data? Or there is a plethora of models out there. How do I pick the best one for my project? So after hearing many questions like this, we identified that there is a common challenge, and that is that there is a need for a clear path through the complexity of the AI development. So our team has taken a hands-on practical approach to tackle this challenge, and by developing an end-to-end AI pipeline that simplifies the AI development process, thus empowering our lab members so that they can effectively utilize AI in their research, even if they only have like a fundamental knowledge of AI. The objectives of this work is to facilitate the integration and adoption of state-of-the-art deep learning techniques and frameworks into our lab's projects, and to develop an efficient, robust, and scalable end-to-end deep learning pipeline that is capable of supporting not only our current needs, but also our future needs. This pipeline consists of workflows that do data acquisition, data pre-processing, model training, and in the future, inference. When we were developing this pipeline, we took into consideration some design principles, such as automation, so that we can enable the handling of tasks that would otherwise be too time-consuming to do manually. Also, scalability to efficiently manage both small-scale and large-scale data sets, and also reusability, so that most of the code base can be used across different projects without requiring substantial overhaul of the code. So let's take a look at the first component, the data acquisition pipeline. And here we require a list with the IDs of the scenes that you want to acquire. Then when the user submits a data request, this list will be equally distributed among many accounts. And then each account will submit an export task job that will export the data from Google Opinion repository to the Google Drive that is linked to that specific account. Then when that data is stored in the Google Drive, we will automatically begin a download task that will retrieve the data from the Google Drive and store TU. Once we have confirmed that the data from the Google Drive to reduce this usage footprint. We have introduced several hooks into this pipeline so that we can handle and catch all of the potential in case we hit the API rate limit. And all these hooks prevent our data acquisition subroutine from crashing, thus making this pipeline very robust. Currently, the pipeline acquires the data from the Google Earth Engine repository, but in the future, we would like to expand our data offer by integrating other APIs such as NASA's Earth Access, as well as Alaska Satellite Facility, so that our team members can have access to a wider range of data from different satellites and different missions. Second is the data preprocessing pipeline. These pipelines allow us to take in a data set that we compose of images of different size, containing outliers, missing values, or that are stored in formats that are not so AI friendly, like GeoTIFF. And we perform a series of transformations, such as splitting into equal size patches, discard the missing values, sheltering, merging, and so on. And also formatting into other file formats like the HDF5 that are much friendly when training AI model. Third is the model training pipeline, and this pipeline was designed to take full advantage of the computing resources that we have at the HPC and NTU. So this allows the user to submit multiple training jobs to the HPC, and because each of the training jobs is communicating to this AI platform called weight and biases, at the end we will have a unified dashboard where you can get a clear picture of how the model is performing under different configurations. So this platform that I mentioned, weight and biases, has some core features that we have found extremely helpful. For example, you can perform real-time performance tracking so that you can see how the model of your the training of your models is going on, and also how much of the computing resources you're consuming. It allows for experiment versioning so that you can keep track of all your experiments and training runs. And it also enables collaborative development across members of the same team. The model training workflow has another key feature, which is the modularity. So by just changing a single line in the configuration file, you are able to swap the model architecture that you are training, and this allows for a very quick testing and comparison of different model architectures effectively. It is also versatile in the sense that it can accommodate training in single GPU environments for quick prototyping of models, and it works also for multi-GPU environments when you decide to scale up and use very large data sets to perform the training. The inference pipeline is still a progress, so it's coming soon. And I would just like to share one of my own research projects about mapping cosines with our intensity data and AI models. So if today I wanted to use this pipeline that I'm presenting, I would be able to go from the first stage, the data acquisition process, to generating the outputs in roughly 3 days. And that involves acquiring over 33,000 pairs of Sentinel-1, Sentinel-2 scene, do the pre-processing, and train the unit model. So in conclusion, we have taken significant steps into developing a scalable, robust, efficient, modular, fully fledged end-to-end deep learning pipeline that consists of, right now, data acquisition, data pre-processing, and model training, and in the future, inference as well. Thank you.
Questions for Noel? Maybe I have a question. Is it open source for? is your framework already open source for everybody to test and try, or?
No, it's not open source yet.
Okay.
So we did alpha test it. So beta test is the natural next step. If there's a need, we could potentially build collaboration and then let others test. And this, and it, we're planning to make it the resource agnostic. So it could potentially be like a supercomputing center or some cloud-based AWS or other systems. So there's that potential. So that
I-
table doesn't have microphone,
I
right?
can shout.
Okay.
So, I have. Oh, oh. Hi, I'm Lina. I'm from SEC. So my question is regarding your third stage, which is on model training pipeline. So you mentioned that it support plug in and plug out any model, right? So, but I'm just curious whether it support the foundation model as well. For example, I can download get a model from Hugging Face. Whether would I be able to plug in plug out with this pipeline as well?
Yes, if it's specifically for semantic segmentation model, if it is from Hugging-Face platform, then yes, you will be able to just import it and change the line, and then the code base will handle all of the transformations that are required to use train this model.
Questions online? I see one chat. Well, what is used to parallelize the processing?
Okay, for the data pre-processing, we're using Fast so that we can submit multiple jobs and just effectively make sure that each job or each node is only handling one subset of the data. Did that answer your question?
So, Jamal from Gallup from NUS. So, what is it about multi-degree? Right, so, for the training and all the pipeline, is it for shared memory or distributed memory?
We're using data distributed parallelism.
Using what are they, so what
PyTorch DBT.
If there is no more question, reach the point for tea break. Exciting. Is the tea ready? Do you know? Oh, thank you. So tea and coffee is ready. So have some caffeine and come back for breakout session. Again, this is the most important event of the day. That's your event. So we have enjoy tea and coffee for 15 minutes and come back to the room at 11:15, please. And for those who are joining online, we will send out our individual worksheets so you can provide your input for the white paper as well. So at your leisure, please complete the form and send back to us later. Thank you.
So if you're downscaling for Taiwan, compare the downscaling for what you not really. Not really. Yeah. We only compare this is the content like this. Okay. So there is a radar.
Systems of biosphere, solid earth, ocean, atmosphere, human, urban systems, and so on. And how can we understand the multiple implications of the perturbation of one aspect of that system and really like going many steps through the chain. So, for example, deforestation results in climate change, which results in sea level rise, which results in changes in tsunami patterns on the coastline. So how do we connect the dots, but do this in a way that we're actually looking at causation rather than correlation, which most of the AI experts said is just very complicated. The next question was, how can we monitor changes in carbon stocks globally and in a robust manner to help with carbon trading and so on? And the challenge that we discussed is that these systems would be based on remote sensing data, but we have to connect them to ground-based observations and proxies. And we're not just talking about above ground carbon, but we're also talking about below ground carbon. So how do we connect the parts of the system to monitor this? And a big topic that came up in every grand challenge for ours was that we can't just fund modeling and AI and remote sensing. We have to fund the basic research and the field investigation that collects the data that we can use for validation and training and so on. We have to do that basic science in order to make any of this worthwhile. And finally, how do we identify anomalous behavior in geophysical systems, such as earthquakes, such as volcanoes, and how do we identify thresholds or tipping points in environmental and ecological systems? And how do we do this using a combination of all the different types of big data that we have to throw at the problem? Yeah, the discussions with AI experts were again the kind of identifying outliers and anomalous behavior might be tricky. And we talked a little bit about causal discovery and causal graphs to try and look at that picture. I don't think that was. That was our 4 grand challenges. Thank you.
Okay, my table 2.
Hello. We first discussed this challenge of information that can only be retrieved by combinatorial. And when you pair the time series of remote sensing data, only when you pair, you retrieve useful information, but not individual epoch of the time series data. How do you train machine and giving, instead of f of ti, you give f of ti, comma tj, and then ask it to produce prediction of f of tx and ty. And here, f is nothing but correlation coefficient. How do we do that? It may as well be already tried and solved. So we've been discussing that. And then how to integrate air quality data at different scale of space and time. Can you use? Can you transfer it? It seems that it's always failing. So it's very challenging topic. And also in biomass estimation, how do we reduce the need for ground truth? If you engage foundation model, what is the right, proper way of designing it? Is multimodal helping at all? And then we started talking about so this list grew with different AI experts visit. We were educated. That's another question. When AI produces predictions, for example, NVIDIA's forecast, decade-long forecast, okay, that's great, but what is the uncertainty? Can even uncertainty be treated as another parameter to be estimated and then be predicted as part of this AI training? And then we learned that ChatGPT has temperature tool, and just like that, we can estimate it. And we just also learned from Savita that there's what is that called? Bayesian neural network to
to estimate both epistemic and aleatory uncertainty, or alternatively, you can do an ensemble approach as well. So that's where we are. Thank you.
Okay, so we have quite a few grandchildren. They're either on climate timescales or weather timescales. So climate timescales is the new culture of AI or something like that. And there's some people in Singapore working on this, but there's already a very established community right on the weather side. So there's a few points here on the climate timescales. The challenge in AI to help reduce uncertainty in climate change projection. Similar with weather predictions, actually, as well. And to enhance the understanding of processes and teleconnection at different times and space scale. Like I think what Emily said in terms of the causal connectivity between some of the key processes that go on between weather and climate. Provide fast and effective climate change attribution systems. So climate change attribution is understanding what drives extreme events, and I think it's a typical great application of AI in helping to boost the sample size to the attribution systems. Enhance the usefulness of weather forecast products to actually contribute to sort of the step up in providing the next generation impact weather products. Develop enhanced interdisciplinary AI. So how to connect different sectors, climate, social, food, economy. So how to connect this, use AI to have a more effective life. Can AI be used to better see tipping points? Emma mentioned tipping points again. And just to find out if AI is any help in looking at tipping points. Can AI do anything to do with these crucial irreversible processes? Use AI to run climate change projections faster, more effective, more sustainable, and with a much larger sample size. So what are the applications of AI in this? And then the better use of weather and climate observations as well. Can we have better observations, produce more but also fill in some gaps. And so I don't know, am I supposed to say the grand challenges or also some of the other ones? So we only have some of the points that we answered here. What's the impact? The impact is better decision making, better preparedness, better communication, overall realistically change behavior of people in the face of climate change threats. So that's what we see as where AI can play a role. Thanks.
So we just focused on two grand challenges, and we invited AIB to give their own perspective, and they're quite different from each other. The first one is about improving inclusive communication to climate science, particularly for low resource languages. So a lot of information out there in text, in recordings, in stories about traditional weather, climate impacts, etc. That's very useful information, especially if you're trying to do. Susan, please interrupt if I'm getting this wrong. So of course there's lots of information out there, lots of data, but it's not a numerical thing, it's a textual thing. So obviously large language models, literally it's in the name, right? You've got other kind of approaches, and we were told by AI so this could solve the problem, so we'll believe them and allow them to solve it. So but the impacts of improving understanding, promoting behavioural changes. We know that some of this stuff is going on in single languages, not necessarily climate change, but we're really sex gender biases in recruitment context. That kind of thing. This AI is already being used for that kind of stuff. So in terms of doing that for getting information out of low resource languages, that felt that this is a good application, specifically for climate science and information, all those stories, those recordings. masses of data available, not your typical data, you think actually know the planet. And that was the first one. Okay. The second one was back to the sort of more traditional stuff we talked about a lot with climate, which was about Drew was the issue about the ocean modeling, and in particular representation of subgrid scale processes, which could be the atmosphere, the land hydrology, and it's a common issue of how you represent things that you can't resolve in your models perfectly. It's an issue for AI models as it is for physical models. Typically, we have tuning parameters and trigger points where we can tune those and we can train our AI systems to better represent those. Typically, that's done to improve the speed to emulate a more expensive, complicated physical scheme. So I think that's the sort of traditional stuff we think about AI. And this is low-hanging fruit. This is the kind of stuff many weather and climate models to do with quite a lot without replacing them. Of course, the impact there, better understanding and improved predictions would be some uncertainty, weather predictions. And Juntao joined us at the end there, and of course, you're already doing this stuff with trained reanalysis data, ocean, purified, so you can train it, but that's okay for the deep oceans and for the large scales, but it's for this part of the world where you're looking at small, local, shallow seas. Two issues. One of the more complicated processes, new processes that are not included, but also there's a lot less data. You can't do anything with that data. So again, so I think on some of the applications in this area, the AI can do more. Maybe at global scales, it can do okay. But kind of the shelf sea stuff, it's pretty useless currently. You still have observations to train, and there's no equivalent reanalysis really to do that. So in that sense, it's much more a hybrid approach, where it goes into just focusing on where you have the data and where the AI can add value to trick functions. Yeah, and I guess why us is the question we all had. I guess it's a general thing, right? And that's why we're all mixing up, is that you've got the expertise in the observations, the processes, and you've got together. And you can't just sit on the table for 2 minutes and solve it. What you need is projects where people come in and work together for 6 to 12 months so they can get a deeper understanding of each other's problems without trying to be the expert. And just bring those people together and in a certain amount of time to solve a grand challenge. But grand challenges are not solved with 3 minutes discussion on the table. So I'll get started. Thank you.
Hi, everyone. I'm a medical doctor, so I cannot find another table except number 5 for me to discuss about. And I'd like to thank Peter for bringing down this because his writing is much more legible than mine. We only have one. Oh, that's good. We only have one vision or dream, and that is to see how we can use AI to predict health outcomes due to extreme weather and climate change. And that could be a long-term exposure and could be extreme weather events that leads to acute reaction in human response. For example, last year we had a lot of wildfire in North America, in Australia, and then immediately caused a huge amount of people going to the hospital and planning for lung diseases and cardiovascular problems. On the other hand, long-term exposure to air pollution would need years of exposure before one gets lung cancer or other chronic diseases. So this could be acute or a chronic problem. But how do we predict what kind of changes will come up with what kind of health events? And the impact is that we will then inform the health policymakers how to allocate the resources to prepare for surprises or prepare for long-term changes in disease epidemiology. So this is our dream and our vision, but we see a lot of challenges that we seek AI experts to help us to answer. First of all, a lot of health outcomes will take years to develop. especially, chronic exposure to, air pollution or water, and so on, or toxic substances in the environment. It won't develop cancer within it will take years. So how do we, recognize that these are the underlying factors and how to address the time lag effect? On the other hand, we find that in the past, a lot of studies are focusing only on physical factors, temperature, rainfall, air quality, and so on, but without taking into account the human factor. On the other hand, we take a lot of physiological parameters without taking into account environmental factors. So in our world of health sciences, we believe that health disease is like an iceberg. What you see is just a very small part of the tip of the iceberg, but 1/3 of the big iceberg is due to genetic factor. 1/3 is due to environmental factor. 1/3 is due to lifestyle factor. And then 10% is because of health policy and healthcare service. So if we just look at the physical or the physiological factor, we are only seeing part of the elephant, but not the whole animal. So how can we combine this together? And I think AI should be giving us a much more capable analytic power to analyze this and predict what's going to be the outcome. But the most difficult issue that we face is when we see A and B exist together, how do we know this is merely correlation or there's a causality in between them, which is the chicken and which is the egg? And that when we pose it to all our AI experts that travel through us, they also find it very difficult. And finally, finding the problem is not our aim. It's to find the solution that can solve those problems. That is our aim. So, but that is only possible when we find out what's the cause instead of what's the correlation. So we learned a few terms today, and we try very hard to understand what that means. But we were told that transformer could be one of the things that can be used to find out which might be the underlying cause of a disease event that we are seeing. It may not be able to pin down to one single factor, but could be narrowing down to a number of factors that we can bring to the laboratory to find a biological solution or a study with animals and so on to work out the mechanism of it. That sounds great. There is something called causal inference or causality network, which again use AI technology to find out possibly which is the cause and which is the cause by the temporal sequence of the events which is happening. But also, most people tell us that the time lag impact is an issue because different people may respond to those climate or external environmental factor at a different time scale. And we have to find ways to really identify and confirm that they are causally related, even though the time is not the same. So for pulse sensitivity analysis and temporal embedding are some of the terms that I would have to work with ChatGPT tonight to find out what they mean. And but those are some of the solutions that they point out. This is the technology that they use with I think the large language model to find out the words and the correlations, the time sequence of it. So anyway, we are seeing some lights, but I think that there's a lot of areas that we can perhaps put as our research questions in the future. Do you have anything to add? Okay, thank you.
Yeah, well aware that I'm standing between us and so it is hopefully very short. I think there are also a couple of papers that mentioned the grand challenges for weather and climate. So I'll just synthesize it together with ours, to summarize it under three broad themes, which we feel our grand challenges would fit under. So where we think AI can help in the weather and climate space would be treatment. So one is AI for weather and climate monitoring. So if you have inverse problems, you have remote sensing data that you need to better monitor the Earth and climate system, AI can come in to help in this sense. Then the second one would be AI for better prediction. So here, better prediction could be of extreme weather, it could be of probabilistic events, uncertainty estimates, it could be deterministic prediction. And the third one would be AI for better climate understanding, weather and climate understanding. So I think Aurel mentioned earlier about attribution studies, leveraging AI to get a larger sample so we can better understand what has happened in the past or what might happen in the future. I think there's been some work also done using AI to understand some of the patterns that happen in the weather as precursors before extreme weather occurs, so that we can apply human interpretation thereafter to better understand the weather. So these are three themes that we highlighted. Why these are so important is because when we look at society, we are able to better predict extreme events, we can react to it, we can mitigate some of the impacts. And I think why we need AI and ML is the two things that we offer is speed and accuracy. More importantly, accuracy, but speed is also of the essence because it allows us to get a better sample for example, AI for better prediction, which is probabilistic estimates. Okay, so this is a summary of our topic that we discussed. Yeah, thanks.
Thank you so much. I believe we had exciting experience talking to each other and connecting our brains. I felt the sparks of neurons and synapses connecting interbrain. So that was a very valuable time. I really appreciate your participation. Before I forget, if you forgot to write down your name, please do so right now on your individual worksheet. Write down your name. And we're gonna have lunch, but before, I want to ask you, this was one of the questions in the registration form when you registered. Are you data hungry? But your data needs are not met, but potentially can be helped with a nudge by NRF to Singapore government. If you have that need, please come see me when the lunch starts. And Eleanor, Yuja, and Steve, and Yuan, if I can have you as a group, I booked a separate room with Martin, 16th floor. So it's about the data talk. Yeah. If you need to leave, just let me know. And like Dale said, this is not an end. This is really a beginning of addressing the grand challenge together. So I think this is a very meaningful moment. Not just people in this room, but also online participants who were not wanting to come. There are a lot of people who wanted to come, but because of this rush and short notice, they couldn't. We want to involve and remember those as a community, and we share our outcome of this feedback. We will also reach out to them and collect their feedback as well, and produce a white paper. In the meantime, please feel free to reach out to us, both Dale and myself, if you have any questions, comments, or any follow-up discussion points. I'm sure from this meeting, we made this connection, we identify who we are, and then continue our discussion together and for collaboration and for grand call. I would like to say special thank you to Kedar, sitting behind. He's been amazingly help us arranging this table and everything. We booked food, tea, coffee, vegetarian menu. All we need